Great. Well, welcome everybody. Today we are very excited to have Beja Azurich presenting their iClear 2022 work, Subspace Regularizers for Few-Shot Class Incremental Learning. Beja is a PhD student in computer science at Boston University working on continual learning, few-shot learning, NLP, and NLP ethics. So we are very excited to hear you talk today. So without further ado, go ahead and go.
Yeah. Hi, everyone. Thanks for having me. This is Faiza once again. Let's go ahead and get started. In this work, we proposed a family of regularization-based approaches to incrementally grow the number of classes a model can predict over. So my collaborators are from my advisor, along with my spouse, actually from MIT. So not sure if you all need motivation for studying continual learning, but here we go for entertainment purposes, I guess. So let's start with considering a real-world example. Think of this imaginary deep learning powered app called Birdie. Given a picture, Birdie can classify 300 bird species it was trained on. With pretty good performance. And let's assume a bird watcher comes across to a new species called mountain bluebird that was not included in the 300 species that Birdie was trained on, unfortunately. So Birdie can make errors. Ideally, even though the model cannot identify mountain bluebird, it should be able to learn it from a few examples if someone were to take a few pictures and provide the correct name. So in few-shot class incremental learning, we test a model's ability to generalize into novel classes without forgetting the old ones, obviously. So what makes this problem hard? Consider the standard neural classification pipeline where a convolutional neural network is followed by a linear classifier. The straightforward way to accommodate more classes is to augment the last linear layer, basically, to make room for the novel class. However, because the training samples are exclusively from novel classes, if you don't store the initial training dataset you used, the scores corresponding to old classes will wind down to zero eventually, resulting in catastrophic forgetting of all classes. So in this work, we focus on a regularization solution and propose two simple fixes. In the first one, which we call subspace regularization, we regularize the novel class representation to lie on the same subspace as the old classes, as defined by the last linear layer of the classifier. And in our second regularizer, we take one step further and incorporate label similarities between classes to better inform the regularization. And I will go into details of these. Before doing so, let's formalize the problem a little more. The first step is to learn a future extractor on the set of base classes denoted by C0. Then in the incremental learning stage, before going into that, we assume that the data set is large and examples are abundant from each class, which is the case for ImageNet, for instance, today. So you can train a pretty decent classifier on the set of base classes. Then in the incremental learning stage, a novel batch of classes is presented. Note that these classes are different from the ones in the base set. And at this stage, we don't assume access to base examples anymore. For memory requirements or like computational requirements, you don't want to like keep them along with you. At the end of each incremental learning session, the evaluation is done over a union of classes seen so far, including the base and the novel classes. Yeah, note also that this there may be multiple rounds of incremental session followed by an evaluation, and every time number of classes keep growing, and the evaluation set is done over all classes. Evaluation is done over all classes. So let's discuss the simple fine-tuning baseline we used based on the initial intuition I described to you. So after initial training, once you have the feature extractor, we continue to use the multi-class logistic regression as our objective function. As you can see here, we assume we freeze the feature extractor. For simplicity, we can talk about it later on this decision. So this is indeed simple logistic regression right now, and the loss is over only the last linear layer denoted by eta. This, we freeze the feature extractor, and this last part is just a weight decay penalty on the parameters of the last linear layer, which were the only ones trainable, and we prevent them from growing too large, standard practice. And this first part is the logistic regression, cross-entropy loss. So let's pay attention to this part where we compute the scores using individual class weights denoted by eta y for class y. Note that this maximization will be done over training samples only from novel classes, as I described. So we don't assume access to training samples from the initial feature extractor training. So this ST is the training set from the novel classes. Yeah, so back to our initial example, ST is composed of examples from Mountain Bluebird. So if you focus on the first part and open the sum up, the individual terms will look like this. We basically maximize this ratio of scores where like this every term in the sum will have the score corresponding to Mountain Bluebird in the nominator, and the scores that vote for all classes will only appear in the denominator. So as we maximize this, these scores will that vote for other birds will wind down to sorry, not sure what happened. Okay, yeah, the second part, like the scores corresponding to other birds will basically wind down to 0 because there is no reason for the optimizer to keep them large. So so while the past work relied on this first part as their baseline, we want to prevent the kind of forgetting that I just described, and add a penalty, a simple penalty called rold as the last term in here. So at session T, rold is for all classes. Yes, rold is for all classes other than those introduced at that particular session T. So we leave all the weights in the last linear layer trainable for expressivity, but at the same time, we prevent them from changing too much from their initially converged values. So as an example, if Mountain Bluebird was introduced in the first incremental session, we and as we progress into the second incremental session, where we see other novel birds, we want to preserve the weights corresponding to Mountain Bluebird. So in this baseline and the following methods I will describe, we use gradient descent because the training set is large as our optimizer, and we train until convergence. So while this is a strong baseline, as we will see, it will not fully prevent catastrophic forgetting. And moreover, it doesn't provide a solution to the overfitting problem that arises due to the fact that we have few examples from the novel class. Which brings us to our first proposed regularizer, Subspace Regularizer. In this one, our underlying intuition is to force the novel representation we want to learn, say for Mountain Bluebird, to share some of the features learned during the base training rather than relying on spurious features that may be learned from the limited number of examples we have from mountain bluebird. In other words, you may need a common set of features in order to describe a bird species. It may be the color, the body, the overall shape. Yeah. So this is the same before we used in Subspace Regularizer with an additional term, which we call RNew. In this regularization, given a novel class representation eta C, we determine a subspace target denoted by MC. And the subspace target is simply the projection of eta C to the subspace spanned by base classes. So by adding our new to our loss, we penalize the difference between eta C and MC. For instance, in this little illustration, on the bottom left, the class weight for the novel class white wolf is pulled towards the subspace spanned by base class representations. And PC0 is simply the projection matrix composed of basis vectors of this space. So moving on to our second proposed regularizer, with the motivation that subspace regularization is helpful in guiding novel weights towards the space spanned by base classes, but it doesn't tell exactly where on this large space that the novel weight should approximately lie. So in our second attempt, we use side information in the form of labels to determine a more informed target on this space, which we call semantic target. So using pre-trained word embeddings, we first compute similarity scores between class labels. For instance, given a novel class label, we compute pairwise similarity scores between a novel class and all base classes. And these scores are then used to compute a semantic target, which is a linear combination of base class weights. And again, similar to previous regularizer, we penalize the difference between the novel class weight and the semantic target, which is a linear combination of base class weights with weights derived from label similarity scores. Yeah. Are there any questions so far? All right.
Crystal clear.
Awesome. Thank you. So moving on. This is the last kind of regularizer we studied. We call it a baseline because it derives a strong inspiration from the zero-shot learning literature. We call this one linear mapping. So we use a standard operation from zero-shot learning works. So after the initial feature extractor training on the base classes, we learn a linear mapping between the language and the visual spaces. And then in the incremental learning stage, given a novel class, we map the label embedding for the novel class, say white wolf in this example, to drive a target in the visual space towards which the regularize the novel class weight. Yeah, so this one is very is making use of a very similar intuition by using labels, but instead of using in pairwise label similarity scores, we learn a mapping between spaces, just as in zero-shot learning. So moving on to the results. So comparing to past work, both our fine-tuning baseline and our subspace regularizer perform better as the number of classes are increased. I have a little animation thanks to Keynote here. And again, when using labels, our semantic subspace regularizer and linear mapping override existing work as the number of classes grow at the very bottom. So despite its simplicity, our subspace regularizers achieve state-of-the-art results on mini and tiered ImageNet, as I'll show in a minute. And we argue that biased regularization around old weights is a promising solution in addressing few-shot class incremental learning. And I will describe another variant we studied. So not all past work assumes zero access to examples from training classes. So some of them keep one exemplar per old class in the memory. So in order to benchmark against them, we consider keeping one example in the memory for memory rehearsal per old class. And we append these examples to our ST, which initially was composed of only novel examples. And we continue fine-tuning the last layer. So the same setup, except the fact that there is a small memory attached. I should also describe the last method here called joint training. In this one, we remove all memory and compute restrictions and keep all previously seen examples in the memory. And at any session where we grow the number of classes from 60 to 65, we retrain a feature extractor and the classifier from scratch end to end. So because of the substantially higher memory and compute requirements, this is rather an upper bound than a baseline. So we call it joint training. So as sessions progress, we observe that our semantic subspace regularization and eventually linear mapping keep up and sometimes override joint training. Yeah, we discussed this. And before the few-shot class incremental learning challenge, there was another thread of research which focused on only a single round of incremental sessions. So you have 100 classes, you want to learn 10 more. That's the challenge. So in that thread, there are multiple notable works, and unfortunately, some of these methods cannot really extend to multiple rounds of incremental sessions. So 100 classes, you learn 10 more, can't extend beyond it. The method doesn't really scale, or it hasn't been shown to scale yet. So for the sake of completeness, we compared to these methods as well. We observed that that only one round is not really enough to show the difference between our regularizers, but it becomes obvious as we have seen as we consider multiple rounds of incremental sessions. But subspace regularization is significantly better than fine-tuning and semantic subspace regularization is better than that in the long run. And here you're going to notice the distinction at the bottom two rows. So here we tried another technique. Instead of just relying on labels for similarity scores, we considered descriptions which come with WordNet. So these are simple one-sentence descriptions of a given class. So we use contextual embeddings, but to be specific instead of labels, and follow the same scheme we use for semantic subspace regularization, compute the similarity scores between classes, and follow the same regularization paradigm. Yeah. excuse me. So this is a distribution of predictions for fine-tuning baseline. Excuse me. So we only show like the first 4 sessions. So the initial number of classes is 60. We increment them by 5 every session. Sorry for the small font, but like here in the y-axis, we see the gold classes. So the first 60 is the base classes, and the next 5 is the novel classes. And on the x-axis, are the predictions. So you're gonna notice that there's like a pretty highlighted clustering at the end, suggesting that like any example is basically classified as one of the novel classes. So this is in literature is called recency bias. So whatever you learn the least, you predict them as such. And that's pretty much the case across like 4 sessions. And at the bottom, we have subspace regularization, where the predictions are more fairly distributed, and like we kind of got rid of that recency bias. So it's more on the x plus y equals 1 axis. And another thing to look at is here is that the errors for like the novel samples are the accuracy among novel samples is slightly higher. You can see like the cloud at the bottom, which may represent a more faithful distribution of errors, as the number of samples is already limited from novel classes compared to base classes, from which we had abundant examples. Yeah. So overall, we argue that the subspace-based regularizers result in a more faithful distribution of errors. And finally, the main takeaways are we found subspace regularization is an effective and lightweight tool to balance stability plasticity dilemma, suggesting that it's a good balance between learning novel classes while preserving performance on all classes under this challenging few-shot class incremental setting. And we also showed that the semantic information is helpful in guiding the regularizer and informing them better. So that's it. Yeah.
Outstanding. Thank you. That was a crystal clear presentation. Everything was wonderful.
Oh, really?
Yes, I very much enjoyed like not just the content but the presentation style. I guess we can open it up now to questions for you.
Yeah, sure.
So anybody who wants to ask a question, if you were on MS Teams, you can unmute and ask it live, or if you were watching from YouTube, you can ask it in the YouTube stream chat. Let me check first. Does anybody on Teams have a question? I see a few people popped off. I'll go ahead and start it up. So I'm wondering the intuitions behind your approach. You use this for few-shot class incremental learning. I was wondering, like, it seemed to me that the ideas of this grounding and subspace regularization could trivially extend to large-scale incremental learning as well. Am I wrong in thinking that, or is that something that's been explored by others, or something that you think could be explored? I specifically, train a large first task for common large-scale incremental learning benchmarks, and then after that large first task, apply the same method using large amounts of data rather than the few-shot case. Do you have any intuitions on whether or not this approach would also aid there potentially?
So there is nothing that prevents technically to apply this method to over there. I believe I just happened to have started with this problem because it had more realistic assumptions to the real world scenario, I presumed. And that is my kind of an intuition. I don't really have an empirical answer because I didn't try in that setup.
I agree with you, though. That makes sense. In those big, large-scale, problems, then you can probably have memory as well. In which case, this is not as needed. But yes, okay, that makes sense. Anybody else have any questions?
Would it work better on task incremental learning instead of class incremental learning? Because in task incremental learning, you can kind of assess the task number or something.
Let's see. Yeah, in task incremental learning, you are given task ID, so you know among which classes you want to classify between, right? So I think if the intuition that some of the features are semantically better, which were learned using more examples in the initial set, is correct, then maybe a regularization approach, which would encourage the novel features to be closer to the semantic features rather than rely on spurious features that may arise in limited number of examples. If you're talking about a few shot scenario. In that sense, I think it could be helpful.
Thank you.
Anybody else? I did have one other question that's not as related to this work, but I noticed you have someone in the chat saying thank you very much for the presentation. So I did have one question. Since you have a strong background or interests in NLP ethics and bias and such, I was wondering if you had any perspective on whether or not in our continual learning kind of niche of research, does continual learning provide more of additional challenges for fairness and bias, or does it potentially bring opportunities to mitigate those further? And it's an open-ended question, and I just wanted to see if you had any perspective on that or not.
Yeah, thanks for the question. So after this project, I wanted to look into how continual learning would look into NLP, which is kind of lagging behind, I should say. And over there, we as the size of the models are getting ever large, preventing them, let alone retraining, but even fine-tuning is expensive sometimes. So there is this idea of zero-shot generalization into novel tasks in NLP. So not sure if you've heard of FLAN or T0, X, T5. So yeah. So those architectures are trained on a bunch of NLP tasks, and people test them if they are good at generalizing into novel ones without any additional data. So this is rather a zero-shot scenario than a continual learning scenario. But over there, I was wondering, okay, so how are these systems doing in terms of social biases in a training task compared to a zero-shot task? So which it hasn't been trained before. So yeah, we have seen an interesting example, an interesting outcome where we observed that the language model was much more biased in the training task compared to a zero-shot task. So without much discrepancy between performances. So say it can do as well as question answering than this task in NLP called natural language inference, where we find if something entails something or contradicts. So the performance discrepancy is not there. So it's doing as well in both tasks, but it's much more biased in the training set, which made me think that, oh, maybe like the training results in language model pick up some correlations which are apparently biased from the way we form the task during training, but like it doesn't really extend into generalization. So which we found interesting. Yeah. So that's kind of the zero shot perspective. And in terms of continual learning, I have been thinking, oh, can we like incorporate so as these systems are interacting with humans, can we incorporate like human feedback, human in the loop kind of a thing, where human could provide feedback into the model based on its like predictions, and like what would be the ways of updating the model so that it doesn't like generate a biased answer again. But updating the language model or any neural network, as most of you will know, it's not a cheap task. So like whatever continual techniques we are, I think, developing for language models, this is an amazing area to try on. Can we incorporate continual learning in order to fix biases embedded in language models, which are extremely expensive to retrain. So continual learning would really help over there.
Yeah, it makes a lot of sense if we can figure out how to basically destroy the bad knowledge while preserving the good performance in a efficient manner than some of these companies that don't seem to care as much. If you tell them they can do it for cheap, then it would help solve the problem a lot. So yeah, I think it's a good way to put it. What's the cheapest way to remove the bias or the bad knowledge while retaining generalized performance? That's continual learning, and basically in a different way.
Yeah.
Thank you very much for sharing your perspective on that.
Chris, thanks for the question. Yeah.
Are there any more questions or chats? Anything? If not, then I guess we can go ahead and wrap up for today. So thank you everybody for joining, especially Faiza for that wonderful and amazing presentation and work. You can catch us again here at the same time next week for a presentation from Martin Munt on Continual Learning Evaluation Assessment Compass to promote research transparency. So we'll see you all again next week.
Thank you.